Now, the second kind of simulation we're going to learn in this course is called spatial simulation. Spatial simulation have to do with human culture issues. Now, one example here is famous Weber's location triangle. This is a business example where you have one company that use two localized material at this two upper point, also produce a final product and ship the product to the market. The issue is where is the best location for this company, and let's set this problem up. So we have 3 points. This one point have one material. This point has another material. This is the market. Where within the triangle the company should be located? Okay, so I can start this random location within the triangle, this random location. So after I let it go, you can see it begin to look for the location where the total shipping cost is minimum. Now, this is the best location. Okay. Now, we can also alter the shipping rate. Let's increase the shipping rate of the final product from 1 to 2. So then you should expect that since the shipping costs for the final product increase, this best location should shift toward this market. Let's see whether that is the case. Okay, again, let's set up a random site within the triangle. This is a random site. Let's go. That obviously you increase the shipping costs for final product. Obviously that make this corner become really optimal location of a production. Now let's make things a little bit more complicated. Let's make the shipping cost of final product increase, but also let's make the material used in material 2, material 1 increase as well. So when you increase the shipping costs of a final product, the best location tend to shift toward this market. But when you increase the weight of the material input for material 1, material 2, it also tend to drag that location back toward these two corners. So let's see what happened. Okay, we set up this random location within the location triangle. The random location is here. Now let's go to see what happened. Okay, the shipping cost still going back this way. Let's try to increase the weight of material 2, material 1 a little bit further to see what happened to the best shipping location. Now the random location is somewhere here. Okay, let it go. Okay, still come back to same place. Let's okay. Let's because come to the corner. So it's become a little. It give the little kind of air and message. Let's do not increase the weight as much. Okay. Also increase the shipping cost of material 1 a little bit. Okay. Now let's see what happened. The random location is somewhere here. Let's see where the factory go. Come to the same corner. Okay, same corner. So obviously we increase the shipping cost very much from 1 to 4. Let's reduce a little bit to see how that would compromise, how this increase the shipping cost of the final product slightly, but increase also the material 1 and material 2. We see how that make the new location come up with a different compromise. Well, moving toward corner 1, because they come to the corner, give you the air messages here. Okay, so that's anyway. That's demonstrate the kind of a model that we can run. This time the material 1 become really heavy. It's 19. Let's make it not that heavy. Okay, let's see. Okay, oh, stop right there. The best location occurred right there. Okay, now this time let's make a little bit toward the corner 2. Okay, see what happened here. Well, stop right there. Okay, so this kind of a model that you can run. We're looking for the best location for a business. Now let's move on to another problem that is a routing problem. Routing problem is something And now we know that during the pandemic, many people buy a product from online, and then company come to deliver the product. When a vehicle has to deliver a product like this problem, if you have uh, 50 locations, 50 customers, okay, we have 50 customers here. Let's set up 50 customers, 50 customers, okay, 50 customers. All of them, you have to deliver them. But starting which point, and you go through what the sequence of delivering that would minimize the time or distance that you make delivery. And that is an issue of routing problem. So the way I solve the problem is this. I'm gonna first I run this model, let's say 100 times. Or let's run this not it take too long. Let's run it 80 times. 80 times. 80 random times. 80 times. Every time it randomly start any particular location, then move on to the next closest and move on to the next closest until it cover all the consumers. And after you run this 80 times, and from the 80 times, it shows the route that use minimum times or use the least distance. So let's start running this model. Okay, let's start set up this model. Let's start the model. Okay, stop this model. Set up this 50 locations. We run first 80 times. Okay, let's start running. Now you can see it start running. Every time it run wrong, it put a one route there. So after you run 80 times, it put 80 different routes there. And after you finish the 80 routes, and you chose the one that give you the minimum distance, that will be the best one. So on the ticks, you can see they run 22, 23, 24, and you wait until it finish 80, and give you different 80 different routes. Then you're going to choose the one that give you the minimum distance. Okay. So you wait until we run 80 times. So it's 40, it's halfway through. You can make this process faster by take this out. This will update. If you do not update view, it can run faster. Okay. You can 60, 63, 64, 65. Okay. So now we come close. $80, so 80. Okay, so now we have 80 the different routes. So after we run 80, you know, the best is we run 80 times. The best one is when we run is 36. So 36. So let's change it to 36. Change it to 36. So 36, the number 36 seems to be the best option. So let's go change the set is to number 36. So 36, and reset it up, run that, and this one you give you the route that number 36. This is optimal. This is the optimal sequence of delivery. You start from this point and go to this point, then go to those customers, and eventually come back. So this is when we have only one vehicle. Now let's say a company is a bigger company that has more than one vehicle to do the delivery. Let's say that we have two vehicles. So the routing problem with two vehicles. We do the same thing. Let's see how many customers. Let's say we have more customers, 100 customers. We set it up 100 customers, and the two vehicles. Let's try how many times. Let's saving some time. Let's try 50 times. 50 times to reduce time. I just demonstrate how do we go about this. Okay, and let it go and start running. It will run two vehicles run 50 times, and each time it calculates its own length of traveling. After it finished 50 times, and we chose the one that gave us the minimum distance, and that would be the optimal routing. So we'll wait until the finish. Now it's 25, 26, 27. So we run 50 times. It's now already 34 times. Okay. 15 more. Okay, so now we have 40. Okay, it's finished. So now it's obviously number 20. So we run 50 times. The number 23 seems to be the best. So now I set at 23. Okay, reset it up and go get the best one. So this is the best route. You have two vehicles. One vehicle run the yellow line, yellow route. Another vehicle run the white route. So this is a vehicle routing problem. You can also have three vehicles, three depots, and so that's similar model, but just three depots. Let me just quickly show you how to do it. So we have 106 consumers, and let's run how many times? Let's run 30 times. Let's save some time. Okay, 30 times. So random times, 30 times. So that after we run 30 times, we choose the one that gave us the minimum length. Okay, let's go. Okay, so now I expect it begin to run, and at the same time you can see they will add this routes from three vehicles. One vehicle use red route, another vehicle use white route, the third one using the yellow route. Okay, so after it's running 30 times, we chose one that gave us the minimum delivery distance. This is a kind of an algorithm that many delivery company is using, and Amazon and also the delivery company and the post office also use this kind of algorithm to determine what is the best delivery routes. UPS as well. Okay, so now it's 8 times because we have 3 vehicles. It will take longer to run each route. Now it's 9 times, 10 times. Okay, and you can see it ticking to give you a sense of a progress. So we run. That's why we only run 30 times to save time, since we are doing only a demonstration. Okay, let's keep running until we finish the 30 routes. So now it's almost halfway through. Now it's 14. 14 and 16. 14 more times. So we can determine what are the best 3 delivery routes for this routing problem. So this is a kind of a program you can learn to run, and this will be very useful for business. 20 times, 10 more times. So $25 times. Almost there. 28, 29, 29. Okay, done. So out of the 30 times, number 5 seems to be the best. Let's set it up to number 5. Reset up and go. So this is solution. Solution. You can see this is a red route is one vehicle, white route for another vehicle, and these the yellow route for the third vehicle. So we have a 3 vehicle routing problem. Okay. Now let's look at this another problem that deal with human cultural issues. Let's talk about migration. Okay, migration is important issue in a sense that it's talk about segregation. Okay, so this is improved. Okay, here is the issue. Here's a migration. So I'm going to set up the 2 communities, one large community, one small community. Both communities have 2 different racial ethnic groups. Blue in these larger communities, the blue is the majority, and with some minority, they're indicating by different colors. But in this smaller community, the pink color is the majority population, and the blue is a minority. So we are going to simulate a situation that you can see the migrants, they have their own colors. Each color indicates different ethnic groups. So these you would expect that the blue color migrant would prefer to migrate to places in the community where you have a blue hosting residents, and the pink migrants would prefer to migrate to the locations where you have the pink existing residents. So this is a kind of a not only migration, but also there's a sense of residential segregation. So let's go. Let's run. So they start moving. Those migrants begin to randomly migrate to move around, and when they come across some part of communities, and within a neighborhood, if there's a certain percentage of residents of their own ethnic or racial groups, they settle down. But if not, they keep looking, and you can see you begin to see these patterns that it seems like that the migrants tend to settle down in a neighborhood where they have a similar racial or ethnic group. By looking at the colors, those pinkish migrants tend to settle down in neighborhood that have same color, it's color of their own. A blue migrants tend to settle down in a neighborhood where the surrounding residents also have their own kind of a color, blue or pink. So that's so to make this process more interesting. Let's also switch on this. This switch asks, do you want to use culture as a draw, as attraction? And let's say yes. Okay. After that, you can really begin to see that each of those migrants begin to move more closely, more quickly toward the neighborhood of their own color. See, that process makes it really faster, and because the cultural draw, they attract to those communities where they see the larger percentage of residents are their own kind. So after the whole process finished, you can look at the residential pattern. Generally, the same kind of group settled together and separate from other groups. In this smaller community, this blue totally surrounded by the pink, and therefore only pink red migrants can settle in those smaller community. But in the larger community, blue migrants tend to settle with the neighborhood with blue, existing residents. So that is kind of a model that you use to show not only the migration, but also the residential segregation. You can also change the size of neighborhood and use the neighborhood of a wider neighborhood to make the process even going faster. Okay. So that kind of model you can do. And finally, let's show a model. Now we're talking about pandemics. Let's show a model that shows disease, spread of diseases. Okay, this is a model that is particularly designed for this event. Let's see. Let me go find that model. Disease model. Spread disease spread. So this is a model that has a lot of buttons here. So I'm going to set up this model. So in this, there are a lot. How many people here? I have 2,500 people there. So they can, you see, those people are red color. These are the people who are already infected, and then. So one person after one person affected, he can go to spread the disease to some other people, and that's why you can see it in a simulation. You can see that some people were dead, they become black somewhere. Some people are recovered, they become green, and let's first run this. Now I will explain something. You can see that those are the people who are green, they have become sick, but they have cured, become green. And those are the people who are dead. I just put them into a black color. And those are the blue are the people who are not affected, not infected. So that's, you also can put some statistics here. This blue line indicated that these are the total number of people. You can see from this size of population, it declined because some people have become infected. And also you see the red line indicates the number of people who got infected. And this green line indicates the number of people who are infected but can cured. The black line indicates the number of people who got sick and eventually died. Okay, now let's change some of the conditions here. Let's see that we have some switches here. Let's switch off. We do not have a quarantine. Do not have quarantine. Do not have mask. Okay. No mask, no quarantine, no lockdown, no quarantine, and no social distancing. Okay. Then let's see what happened. How many people were affected in the first place? Initial infection rate is 43 per 1,000 people. So let's set it up. Okay, let's see what happened here. Okay, you can see that the dead people increase. A lot of dead. Those migrant, those people who are not moving, that means they're dead. They're dead. And you can see that the blue line drops more significantly. That means that those remain healthy people is a lot less. And the more in the red line go higher, more people are affected. The black line also increase. That means that the more people died. So that is when there's no social distancing, no lockdown, no quarantine, more people died. Now we can make more people, and instead of 2,500 people, let's make 3,000 people, and increase the initial infection rate to 50 is to 100 per 1,000, 100 per 1,000. Okay, more people, okay, and also make the later infection rate also become higher. So then you would expect more people to die. Okay, okay, set up and go. So you can see more people died. So this blue line dropped dramatically, and more people get sick, and less people keep healthy. Okay, so now you can see the bodies littered all over the place. Okay, so that is kind of, and yeah, some statistics you can read from these monitors. Okay, so now finally you can see how many people I see that are up without social distancing, without lockdown, without quarantine. You have out of 3,000 people, and you have a total infected 2,175 are infected, and total sick is almost 2,000 get sick, and 4 people just cured by themselves. And how many people died? 1,089 people died. Okay, so that's give us some statistics there. Now let's say that if we have lockdown, and see what happened. If we have lockdown, remember now we have 1,089 people died. Good, set it up, and we go. Lockdown means that people cannot move as freely as before. Okay, let's see what happened to lockdown. Okay, do we have deaths increase or decrease? Well, it's you have a deaths, number of deaths increase. Seem to not quite go to intuition. Lockdown means that people are trapped in a space, and so that you if anybody gets sick in a small space, it's more likely that they will impact people here. So your lockdown is not enough. In the further lockdown, okay, we further lockdown is that we have even build up even smaller area. People can only move around in a smaller space. Let's see what happened here and go. Okay, let's see what happened to the death. So this time we have still over 1,000 deaths already. You see, we still have over 1,000 deaths. That means just lockdown is not enough because people can still move in a small area. If there's anybody sick here, and but they can still move within this area, so they can still infect other people. That's why you need to have you need a social distancing. Now let's turn on social distancing because you lock down. You also social distancing. Now let's see what happened. Again, 3,000 people, same initial infection rate and same later infection rate. Let's see what happened here. So now this time we not only lock down, but also with social distancing. Much better. So we have less than 1,000 deaths, less than 1,000 deaths. That indeed improves. So you need to not only lock down, but also you need to make sure your social distancing. And so that is something that give you a sense of what we can do. What about we also quarantine for those people who are infected? Let's trap them. Do not let them move around. So that let's see. We turn on the quarantine. Not only we lock down, do not let everybody freely move around, but also we keep distance from each other. In addition, we keep those people who are infected in kind of centralized places. Let's see what happened. Okay. So we put them in the middle put those infected in the middle. Now you can really see it, that the deaths become really, really low. We've only have 269 deaths, and a lot better. So this is the kind of model that we can use to just simulate what is happening now. Okay, so this is the kind of stuff that you can do with this course that cover both environmental simulation and spatial simulation. So I hope this highlights some of the major the material that we're going to learn in this course, and hopefully you guys can sign up for this course. We learn about this stuff. Finally, before I let you go, let's do one more fun thing. I know you guys play computer games, so I'm going to show you a game that you can produce by using this program. This is called bombing. So this is a game called bombing. So I'm going to bring up a few bombing simulation. It's just airplane, the bomb other, bomb some object on the ground. Okay, let me do flying, bombing. Okay, maybe this is the one. Let's see whether this is the one. Okay, this is you have one house, and this airplane. Well, you can just get a house. Let's go to some more fun thing. So that is the one bombing. That is a number just bombing. Okay, let's go to number 2. Look at this. Look at this. Okay, now we have this space, and we have a moving target. Well, moving target, and every time when this move, the missed, it keep come back to get it. Come back to get it, because I see it come back many times, and because you see a slider, I only set its accuracy rate is 1 out of 10. So that's why they go after this target many times and try to get it. So eventually, 1 out of 10 time it may get it, or not get it. Get it. Now let's use the slider to increase the accuracy to make it 50%. So 1 out of 2 time it may get it. So let's see the bombing. Boom, got it. I got it. Okay, now try again. Well, you got it again. And you see, ooh, miss it. Come back to get it. Ooh, well, you got it. Okay, so the moving target. Now let's try one more thing. I tried this one, that is the vehicle could move in both directions, not just in one direction. In one direction, it's easy to get it, but what the vehicle could randomly move in both directions. Okay, this one, before we run out, let me show you this one. This one is simple. It's a steel target. Boom, missed that, come back again. Well, yeah, with low accuracy rate, keep coming back. It's 2 out of 10. You can hit it. Therefore, they repeatedly come back to hit it. And okay, finally got it. So if we increase the accuracy rate to 50%, 5 out of 10, let's see what happens. The steel target, boom, got it. And got it, good. Now let's try the vehicle can randomly moving in both directions, not just in one direction. In one direction is relatively easier. What if we have a vehicle moving target that can move in both directions? Okay, this one. Okay, let's see. Let's reduce the accuracy rate to 3 out of 10. Go. Okay, this is still in one direction. Okay, let's go back to the vehicle can moving randomly in both directions. And bombing, number 4. So that is a fun thing. Okay, 50% chance. Okay, so it moving. You can see that it's quickly moving both directions, and therefore you can see that this bomb also switch back and forth. Let's reduce the accuracy rate to 3 out of 10. Oop, it means several times, but keep coming back. Eventually got it. Okay, and got it, and this time. Keep coming many times, eventually you got it. But we increase it to 6 out of 10. One time you got it. So this is the kind of stuff that you can get. You can learn in this course, environmental simulation and spatial simulation, and that's also have some fun to develop your own game. And that is what we do in GEOG454. I hope you guys sign up for the course, and we're gonna have fun in this course. Okay, thank you very much. I hope I see you in the course.